Okay, so we are moving on to the next speaker that I have the pleasure of introducing, who I do not know yet. Very excited to meet Gary Gordon. I am going, oh, hi, there we go. Okay, hold on, hold on. There you are. Hi, nice to meet you.
Hi, is the audio working?
You sound great. You are ready. You're looking good. Great background, lots of sunlight. You are ready to go. And I'm about to give you the intro of a lifetime.
Okay.
Are you ready?
Yes.
All right, everyone. Gary Gordon is from Miami, and he received his BA from the University of Florida in 1977 and his PhD from the University of North Carolina in 82. His mathematical interests include combinatorics, geometry, and algebra. He's won awards for his teaching and his research and is proud to have served as a posse mentor. Oh, hold on one second, just a little zoom sitch. There we go. He ran Lafayette's REU program from 2000 to 2010 and has published extensively with undergrads, and he edited the problem column in Math Horizons before Glenn Whitney took over in 2018. He enjoys all sorts of games, but generally loses to his wife and frequent mathematical collaborator, Liz McMahon, and to his two daughters, Rebecca and Hannah. The four of them co-authored a book on math of the card game Set, The Joy of Set. He is the slowest set player in the family by far. So guys, from the articles I've read, Gary doesn't love when people make a big fuss about him, which I totally get. But I will say that in doing my research, the one thing that stood out over and over again were how great your reviews were on ratemyprofessors.com. And I'm gonna take the liberty of just reading a couple out right now because I'll tell you, it's not often. Sometimes when you go to ratemyprofessors.com, it can be a dark place. But I want to tell you guys that Gary Gordon has 100% rating of I would take a course with him again. That's pretty amazing. And I'm just going to read a couple of my favorites. Because honestly, really, guys, there's one thing to be a mathematician, and that is great. It is great. But a math teacher changed my life. And when I meet other math teachers who have so clearly affected their lives of their students, Gary, I know you don't like a fuss or whatever, but we're going to make a fuss. All right, here we go. May 8th, 2020. I can honestly say he is the best professor I've ever had, and I'm not usually a math person. He is the sweetest and most caring teacher I've encountered and made me excited for class. I wish all my professors carried themselves with the same energy and passion for the subject. He's very accessible outside of class and always willing to help. I mean, like, are we crying? I'm crying. Okay, just a couple more, a couple more. One of my best teachers at Lafayette, awesome guy, and an even better professor. And finally, oh no, okay, two more. We're reading two more. Don't kill me, Gary. Just two more. This guy is a model for an excellent professor. He's approachable, helpful, excited about what he teaches, and truly cares about his students. And finally, best teacher ever. If you never took calculus, I recommend you taking Professor Gordon's class. He's helpful, funny, and very interested in his subject. He always wants to help students as much as he can and does whatever he can to help you understand the material. How are you, like, that's amazing. Did you bribe anyone? How'd you get
Yeah,
those?
that's really sweet. Well, they limit how many you can contribute yourself. So, um, no,
Nice.
yeah, I feel like I should stop now. That was really sweet. Thank you,
How many
Vanessa. That's
email accounts have you made up just to leave all those reviews?
yeah.
Well, honestly, I think it's amazing. All of us are excited to hear you speak, and being kind and thoughtful and funny and always willing to help are some of the literal best compliments a teacher can get. So, um, thanks for being you and for adding to helping everyone feel included in the math community. I'll pass it on over to you.
Okay, thanks so much, Vanessa, and thanks to everybody. That was a really, really sweet introduction. I'm going to try to share my screen, and let's see if this works. Let's get this to be full screen.
Killing it.
So there have been some really interesting talks about a lot of different things. One feature of this talk, I think, is going to be that if you're bored with what I'm doing, just wait 5 minutes, it's going to change. What I want to do is talk about math contest problems. And these are problems, sometimes they turn kids off, but sometimes they turn kids on. And it's a nice way for a lot of students of different ages to get excited about math. And I think for me, this kind of goes back to that lovely introduction. I always love math. It was interesting for me to hear about Ian this morning or this afternoon, depending on where you are, or this evening, talking about what drew him to math when he was young, and he always had that interest. I always had an interest in math, and teaching was more of an acquired taste. Once you realize sort of the purpose of teaching is not to teach calculus, but to teach people, then that sort of opened a door for me. I was also very fortunate to have my wife, Liz McMahon, who's going to be speaking later, be such a positive influence for me as a teacher. So, okay, so let's get going. These are, so the first question I would say is, why do you study math? Now, most of the people in, I hope in this audience don't need convincing, but one of the things that draws people to math is, well, there's always the money part. Math majors do, STEM majors in general are among the best paid majors. But from the point of view of comparing this to, say, history or English, you don't need to read really long books. I mean, there are really long math books, but you generally don't read them. You don't have to write long papers. You write problem sets. And finally, problem solving is fun. So that's sort of the theme of this talk. Problem solving is fun. And what I'm going to do is I'm going to give you lots and lots of different problems. I'm going to try to classify them as very, very subjective in terms of what I think is interesting and what I think is maybe a little bit boring. But we'll start with, what's the difference between a good problem and a bad problem? A good problem should be easy to state and understand. You want to make a problem so that everybody can understand it without having a lot of specialized knowledge. So it shouldn't require that. It should be easy to get started on and to get some ideas for. And if it's a really nice problem, there's an aha moment that solves the problem. So here's my first example of something that I would call an aha moment. Some of the problems I'm going to show you are old problems that have been around for a while. You may have seen some of these before. Some of them are probably going to be new. So you have 100 ants on a 1 foot long table. So think of it really as just a one-dimensional problem. They're just walking back and forth along this line segment. And they walk at a rate of 1 inch per second. When the ants hit each other, they turn around. So if you've got two ants going, they're walking toward each other at the same speed. At the instant they hit, they just turn around. What's the question? How long will it take for the ants to fall off the table? And here are 4 answers. So I say it's 1 foot and they're moving at 1 inch per second. So 12 seconds is a reasonable guess. 1,200 seconds. Well, I guess I took 100 and I multiplied by 12. Maybe that's the right answer. The third one is kind of an interesting choice. They can be trapped forever. And then the fourth one, I just love this picture of ants over Shanghai. I need to find the artist, but they're flying. And as Vanessa said, I'm from Miami, and in Miami, every insect flies. Ants, roaches, they all fly. The ants that fly there, I think, are called termites. So I don't know if you guys have a question, if there's any way I could sort of take a poll, but
you can ask a question, and some of the people in the Zoom room can answer. We have a bunch of people on the chat.
People can also sign into the form, and they can fill in their answer on the form as well.
Yep, I'm monitoring the Google form, which is on.
Okay, so you're doing that. I'm not.
I've got it.
Okay.
I'm on monitoring duty.
All right.
But Gary, could I just ask a quick question? Your question says, how long will it take for the ants to fall off the table? Is that for all of the ants to fall off the table?
Yes, good question. I want all of the ants off the table, not one ant, but I want them all off the table. And you can imagine that it's possible, at least in theory, that maybe there's an ant that's constantly trapped in the middle, keeps walking and then hits something and then turns around and walks and he goes in the other direction. So
this is hitting too close to home because right now I have an ant infestation in my bedroom. I've just got to say.
Hey, at least they're not roaches. Okay.
Oh God. Okay. Yeah. We're ready.
All right. So here's the solution. So I'm not giving you a lot of time to think about this. But the thing I love about this solution is there's a beautiful aha. When the two ants, so think of just 2 ants on the table. When they meet, they turn around. What does it look like after they turn around? Well, if you look at the second and the third picture here, these little cartoons, here they're meeting, and now they have turned around. But it's indistinguishable from them walking through each other. as far as I can tell, and I don't care which ant is which, they might, but I don't. They probably don't either. That picture means that I can just envision the entire problem as the ants are just walking and they never change direction. And if they encounter another ant, they just walk right through it and they don't slow down. As soon as you have that insight, then the answer is clear. It takes 12 seconds because every one of those ants is going to fall off the table in less than 12 seconds. To me, that's a beautiful aha. I think the first time I talked about this problem with one of my daughters, it was a good indication that she really liked math, although we already knew that. Her response when she saw that is, oh, that's beautiful. That idea is a really beautiful idea. And one of the themes in this talk is that if you do get a good idea, hold on to it. Keep it somewhere in your brain. It might help you in a future problem. Okay. This is a different kind of problem. The segues in this talk are going to be probably a little clunky, meaning that I'm going to say, here's a problem. Oh, that was fun. Here's another problem. Oh, that was fun. There will be some theme, though, that goes through. Students really like logic problems. In this one, I have 3 rooms. One room has a bar of gold. One room has a tiger. There should be an Oxford comma there. And the third room is empty. So furthermore, the signs on the doors of the room, there are signs on each room door. And the one that contains the bar of gold, that sign is true. The sign that contains the tiger is false. And the sign on the empty room could be either true or false. And here are the 3 rooms and the 3 signs, and you're supposed to figure out which room is which. You want to find the gold. So this was originally, I think, a lady or a tiger problem, but we might as well update that. So here's the solution. And again, I'm sort of taking away your fun. And if you're interested in doing this yourself, put your fingers in your ears and hum loudly and close your eyes, and you can do it. So it's sort of a, let's just check the possibility. So I'm going to figure out where the gold is. Could the gold be in room 1? If it were in room 1, then the sign on room 1 door that says this room is empty has to be true. But if it's true, that means the room is empty, which means the room, it can't be in room 1. So that leads to a contradiction. So we stop with that. So the gold can't be in room 1. Could it be in room 2? If it were, then the tiger would have to be in room 3 because that would have to be a true sign. So that means that room 3, which says room 1 is empty, is a false statement, which means that room 1 is not empty. So it means that room 3 and room 1 I'm sorry. Room 1 must be empty because the tiger is in room 3 and the gold is in room 2. So that means that the sign on room 3 is true, but we know it's false because it has the tiger. And then finally, is it in room 3? The answer is, I sure hope so. And you can check and everything works out. So there are bigger versions of this. I'm not going to go through the solution to this one, but this one has 9 rooms. You can see the 9 signs. It's the same rule that the empty rooms have something that's either true or false. The gold has a true statement and the tiger has a false statement. There's exactly 1 gold room and 1 tiger room. You're supposed to find the bar of gold again. But unfortunately, even with this information, it's not enough. But if I also tell you that room 8 is not empty, this one, then you can do it. These are pretty ingenious puzzles. And the person who invented them is a famous logician named Raymond Smullyan, who died a couple of years ago. Had a long and very, very interesting and prolific career. A logician. He was a good enough pianist that he could have been a professional pianist, they say. And a logician. He dropped out of high school and taught himself math. I think he was actually awarded his undergraduate degree, even though he was 1 course short. The 1 course short was calculus, and he was teaching calculus at the time. So interesting, interesting guy. What is the name of this book is probably his most famous book. Lots of really beautiful logic puzzles. So here's really where I want to sort of concentrate for the rest of this presentation. I like to think of problems as sort of the question is interesting. So what is an interesting question? It means it's something that sort of catches your attention. An interesting solution is one that I think you're surprised by, and it maybe has that aha moment. Unfortunately, there aren't as many questions, problems in category A as I would like. And every possibility here in this little 2x2 array can occur. So I'm going to try to convince you and give you examples of all four kinds of problems. And I'll actually go through some of the solutions, but pretty quickly. So here's A. I'm going to choose two positive integers at random. What's the probability that they're relatively prime? So relatively prime means they have no common factors. So it seems like a kind of a nice question. It turns out to have a really pretty answer. It'll connect to something that Glenn Whitney said this morning in their very fun talk with Alyssa Crayons. Here's another one. I think of this problem as reasonably interesting, and the solution is not really boring, but it's you draw a bunch of lines in the plane and you want to know how many regions they create. A three-dimensional version of this might be you have a cube of cheese and you slice it with a knife and you never reassemble it. You just keep slicing. And the question is, if you slice it 100 times, how many little bits of cheese can you have? A boring question with a surprisingly interesting solution is this one. Is the number 8051 a prime number? And then here's a boring question with a boring solution that we give in our calculus class. Find the derivative of that function. Okay. So I'm going to try to convince you that this is an interesting question, an interesting problem with an interesting solution. So our 9 and 14. So just to make sure everybody is on the same page, what's the probability they're both relatively prime? 9 and 14 are relatively prime. 12 and 21 are not because they share a factor of 3. So I'm going to outline how you do this. I'm going to skip some steps. So the fundamental idea, this is a standard idea in probability, but the idea is that the probability of success plus the probability of failure is 100%. Here's what we're going to do. We're just going to sort of break the problem down into pieces. How could it fail? How could they not be relatively prime? Well, they might both be even. And there's a 50-50 chance the first number is even and a 50-50 chance the second number is even. So there's a 1 in 4 chance that they're both even. So the probability that they're not both even, and here I'm using the probability of failure is 1 minus the probability of success, is 1 minus a quarter. And then you do the same thing for multiples of 3 and multiples of 5. Notice I skipped 4. I don't care if they're multiples of 4 or not because I've already checked if they're both even. So if they happen to both be multiples of 4, then they were even, and I've already taken care of that case. So what I'm going to do is I'm going to take these 1 minus a quarter and 1 minus a ninth and 1 minus a 25th and keep going with those. And I'm going to multiply them all together because in order for them to be relatively prime, they can't both be even, they can't both be multiples of 3, and they can't be both multiples of 5, and they can't both be multiples of 7, and so on. All those ands in probability means I multiply. These are separate events. Think of them as independent events. You can do a little bit of work. It's actually not too bad, and it's kind of fun to go through and show that that expression, that infinite product, whatever it means, can be rewritten as this quotient where the bottom is an infinite sum. If you have questions about going from this step to this step, and I would say just sort of play around. You need some infinite series things. And what you want to do is you want to flip this. You want to look at the reciprocal and use power series for each one of the terms, 1 over 1 minus a quarter and 1 over 1 minus a ninth and so on. So here it is. Now this bottom should look familiar. That was what Glenn Whitney was looking at today when he was looking at one of these questions involving pi. This is due to Euler, so it goes back, well, to the 1700s. The sum of the bottom is pi squared over 6. So the probability is 1 over that, which is 6 over pi squared, which is around 61%. So it's actually more likely that they'll be relatively prime than not. I don't know how interesting that is, but I think the 6 over pi squared is a really beautiful answer, especially on March 14th. So, okay. I claim that this was an interesting problem with a boring solution, but one thing I do want to emphasize with this problem is it gives you a good way to attack a problem. When you have, when you're given a problem and it's got some number in there and you don't know the answer, I would say a very standard and very productive trick is to start doing small examples and look for patterns. So one line gives me 2 regions. 2 lines is going to give me 4 regions. 3 lines, it turns out, gives me 7. And you can draw these pictures. 4 gives me 11. 5 gives me 16. And there's a picture of 16, and you can count them. It turns out these 5 lines have 10 infinite regions that sort of go out the outside. And there are 1, 2, 3, 4, 5 in the interior. 6. Good. 16. And now the question is, do you see a pattern? And the answer is, well, if I add 2 here and then 3, if I look at these pairwise differences, 4, 5, I see the pattern. And then there's standard techniques for figuring it out. It turns out the answer is this quadratic expression in n, if you have n. So for 100, this would be 100 squared plus 100 plus 2 divided by 2. So somewhere around 5,000 regions. Here's a boring problem with an interesting solution. It's quick. Is this a prime number? No. Here's the reason. 8,051 is 8,100 minus 49. 8,100 is 90 squared, and 49 is 7 squared. I've now written this as a difference of 2 squares, and now I can just use this elementary algebra fact that a squared minus b squared is a minus b times a plus b to get the factorization. I went to a talk once where a very famous number theorist, Karl Pomerantz, was talking about factoring integers, and he said he got this problem once on a math contest when he was in high school. And he wasn't able to do it. He kept trying different numbers, and he had 1 minute to do it. It's a cute trick, and it's just, you're taking advantage of this really elementary algebra thing. I will say, though, if anybody asks you is, and then they have a big number, a prime number, and they expect you to get the answer has to be no. Because if it were prime, there's basically not a really quick way to check it in your head, at least that I know of. This is a boring problem and answer. So again, it's subjective, but I think the solution is kind of interesting. I've got a pool table. The dimensions are A by B. And there are holes in the 4 corners. I'm ignoring the sides. A ball is shot from one corner of the table at a 45-degree angle, and then it bounces with these perfect angle of incidence and angle of reflection being equal. So here it bounces and then bounces and then bounces and then bounces, and you can see it's there it is now. How many times will it bounce off a cushion before it lands in a pocket? This has got a beautiful solution, and what you do, instead of trying to keep track of what's going on inside that one rectangle, what I'm going to do is I'm going to unfold the pool table so that it fills the entire plane. And now, instead of reflecting when I hit a wall, I'm just going to keep going. So hitting at this point corresponds to that point. Hitting up here corresponds to hitting down here. So now the question is, when do I hit a corner point? Something that's a multiple of A is the x coordinate's a multiple of A and the y coordinate's a multiple of B. And that's really not hard to figure out. It turns out that's the answer. I don't think the question is terribly exciting, and the answer is just an answer. But the solution technique, I think, is a really nice technique. And it's useful in other things. I don't think anybody will dispute that this is a boring problem and its solution is boring. In fact, that would be the best answer. If I had a student who wrote that on a test, I would be tempted to give them full credit. I didn't even bother doing it. What I did was I threw it into Mathematica. So I don't know what that message that sends to students or listeners to this talk, but that's an answer. So I got involved in problem solving. It was always an attraction, and I liked working on problems and occasionally creating my own interesting problems. In 2013, Derek Smith, who's a colleague of mine at Lafayette, had been editing the problem section of Math Horizons, and he'd been doing it for 5 years. And he asked me if I'd like to take over. And my response was yes, but I was a little bit, I was nervous about it because, you know, you're going into something at least I was feeling like I needed to make sure that the problems were really well vetted. Didn't always happen, but this is what the playground looks like. So you can see there are usually 4 problems per issue, sometimes 5. And then there's this carousel, which is an oldie but goodie. I'll talk a little bit more about that in a minute. Derek is the person, my colleague is the person who came up with the idea of calling this the playground. And I'm pretty sure the reason he did that is he had 2 kids who were both less than 10 at the time that he was doing this. So he spent a lot of time at playgrounds. He's got a section in there called cleaning up. He had another section, 5 more minutes. It was very much my kids are in a playground. So here's a question. This is the easiest question that I think I've got. There are 4 issues of Math Horizons per year. I needed 4 new problems per issue, and I did this job for 5 years. So how many problems did I put in the journal? That's the answer. I call that a boring problem in terms of the question here, and an absolutely terrifying answer. The 2 weeks before I had to submit my problems to Dave Richson was the editor for most of the time I was there. He was a terrific editor. There was a 2 to 3 week period where I was frantically working problems and trying to find ones and trying to tweak them to put together a good column. One of the first ones that I did, this is a problem that I sort of borrowed from seeing somewhere else, is a teacher writes a bunch of numbers, 1, 2, 3, consecutive numbers on a piece of paper. They stop eventually, but they don't tell you when they stop. Then the teacher erases one of the numbers and tells you that the average of the remaining numbers is 72 and 23/24. From that information, I claim you can figure out how many numbers the teacher wrote down and what number was erased. And since I'm not standing in a room with a bunch of people, but instead yelling at my computer, I can't really tell if you guys want to work on this. But what I will do is tell you that 72 and 23/24 is that number. The average is, this should be about half. I know what the average of the numbers 1 through anything are, 1 through n. So this tells us that the number n that we wrote down should be about twice this. And then you can sort of go through some small case analysis to figure out there were actually 145 numbers, and the number that was erased was 79. And if you want to play around with this problem, you can change this fraction and see if you could challenge a friend and see if they could figure it out. Kind of fun. Here's a problem construction. First of all, this is a picture of my gas tank. I want you to know that the speed was 0. I was sitting in the car. It was not moving. So I wasn't taking a picture of my speedometer as I was driving 75 down the highway. What I want you to pay attention to, though, is the gas tank. So I was looking at the gas tank, and I was trying to figure out, is this pointing to, it's not one of the, 1/2. This would be 5/8, 3/4, and so on. Is this really 2/3 or at 5/8? So sort of close. Maybe you could convince yourself it's closer to 2/3, but maybe maybe my eyes are tricking me. 5/8 is over there. So somehow from that gas tank question, I was driving with Liz. We were going to a conference, and we were going to be talking. And I said, hey, this looks like sort of a fun question. I wonder if I could convert 5/8 to 2/3 or 2/3 to 5/8 by just playing around with the fractions. So I came up with this gas tank fraction problem. So it's really joint with Liz. So you're given a positive rational number and you write it in lowest terms. And here's the game. You can transform your rational number by adding either one to either the top or the bottom of the fraction, and then you reduce. So I want to show how I can go from 5/8 to 2/3. So 5/8, and what I happened to do here is I went to 6/8, reduced it to 3/4. then 3/5, then 3/6, that reduced to a half, then a third, then 2/3. So that's one way to do it. It's not the only way to do it. And again, if I were giving this talk in person, I might say, okay, take 5 minutes, work with a friend, show how to get from 8/13 to 5/6, or make up your own problem and challenge your neighbor, which would be kind of a fun one to do. And then the general problem, which, so is sort of suggested by this, is if I have any two rational numbers, can I always get from one to the other? And in math, that means if it's true, you need a proof. If it's false, you need a specific counterexample. That's the way math works. So I'm going to show you how to get from 8/13 to 5/6. So I'm going to start by adding numbers on the bottom until I get a half. Okay, can I always do that? I hope so. Now I'm going to go from 1/2 to 1/11. Why did I stop at 1/11 instead of 1/6 or 1/12? Well, because they don't work. And now I go from 1/11 up to 10/11, and then finally I'm ready to add 1 to the denominator, and it gives me 10/12, and there's 5/6. The general procedure, if your target is a over b, what you want to do is first transform your fraction to a half. Okay, so you got to convince yourself you can always do that. It's not too hard and it's kind of fun. Then you need to find a prime number that's one less than a multiple of the bottom b. I'm not going to tell you why this is true. It turns out you can always find one of these, and the reason is theorem of Dirichlet, who was a mathematician who lived in the late 1800s. And he proved that you can always find a prime that's one. He actually proved more than this, but this is one of the things that falls out of that. One less than a multiple of b. Now I'm going to add 1 to the top until the top looks like k times a. And the bottom, remember, is k times b minus 1. And then finally, I'm just going to add 1 to the bottom. And then the k's cancel and I get a over b. So that's the general procedure. This is sort of a game that also involves rational numbers. I'm not showing you this because I care about this problem at all. But what I am going to show you is what I gave this problem years ago to a group of students. And this was my favorite solution. The solution was written on a pumpkin. This is Katie. And Katie went to, this was a team. They were a math team at Lafayette. The three of them were working together. Katie went to grad school in chemistry at Stanford. Jorge went to, I think, University of Washington to do math in grad school. And Xing went to Harvard Law School after an undergraduate math major. So it's kind of interesting that these three kids did three different things, but all of them were math majors at Lafayette. This is sort of a picture of their solution. I got the best picture I could. And Katie is the one who wrote this. The solution's correct. She said she had to go over each letter 2 or 3 times in order to get it legible. And I sent the picture to the people at Focus, which is another MAA journal. It's a newsletter. It's really fun to read. The only question I have for them is why on earth they put a pumpkin with this fall background in the June-July issue. So it's not fall anywhere.
I would say my bigger question, I'm not sure if anyone else is thinking this, but why? Why a pumpkin?
So as my problems got stranger and stranger, this group decided to sort of push the envelope of what they could do for solutions. I think one of them was like a one-act play that they filmed. One of them was, this was sort of the most creative. This was certainly the heaviest.
Okay, but a one-act play, that sounds real. Like, I'd love to see that. That's kind of what a TikTok video is, by the way. A one-act play.
I guess you're right. Yeah, you're right. Sort of the right amount of time. You don't get bored.
Yeah. But that's also such a cool idea to give students these really unique ways to present solutions.
Well, what I would try to do with these problems is phrase them in a way that would get the kids excited and make it fun. For example, one of them was a standard there are three people that are talking, and one always tells the truth and one always lies, and one you can't tell, sort of like that logic puzzle with the room signs. But I changed it so that somebody stole a calculus book, and that was sort of the puzzle or the game. So they kind of get involved in these, and it doesn't matter how corny the stories are, the kids really like them. But this one, the solution was much better than the problem. So
it's a pretty, I don't know how that didn't smudge. I feel like I would have been so mad if I was writing that and there was a smudge on it. It looks perfect.
Her handwriting on tests and homework was the same. It's just beautiful handwriting.
Like nothing is crossed out. I'm looking really close. Was there any mistakes?
No. And you can see here, there's a little black box, which means you finished that part of the proof. Yeah. So
stunning.
This is supposed to show you it's not all fun and games. So one of the things I wanted to do was say, look, I'm trying to tell you what I think is a fun game, and what's a fun problem and what's not. And there are other ways to tell. So this is a problem that I posed. We published this in Math Magazine with a student, Peter McGrath. Peter at the time was an undergrad at Lafayette. He ended up getting his PhD and is now a professor, I think at North Carolina State University. Terrific student. So this was sort of like motivated by the alternating series 1 minus a half plus a third minus a fourth and so on, which converges to log 2. But here I said, well, what happens if you take a chunk and add them, and then subtract a chunk, the same size chunk, and then add the next chunk, and then subtract the next chunk? What happens there? Well, the solution came, so in these journals you get, and I had the same thing in Math Horizons, you get solutions from people potentially all over the world. So the solution was from this guy in France. And let me get back to the right page. And so I don't care too much about this, at least not for now. He did some work. And then at the end of the solution, the editor had done some work and said there are connections to a few things that had been published. This was published in 2012. This was connected to something else. But the real thing I want to emphasize is the bottom here, also solved by. So this is a list of all the people who solved the problem. There's somebody in Greece, there's somebody in Syria, somebody in Australia, somebody in Germany. Problem-solving teams from a couple of universities in the United States. There's Northwestern and Texas State. There were 11 incomplete or incorrect solutions. It's nice, I guess, that they didn't publish the names of those people, but the problem attracted a lot of attention. So the marketplace answer is, yeah, this was a good problem. And you don't know before you start. You may have some sort of a guess that this is good, but maybe you're wrong. Let me give you another example. I love this problem. So here's the idea. I draw a bunch of points in the plane and I make this thing that looks kind of like a jungle gym. And some of the points are collinear and some of them are not. Note that point A is on a 3-point line and a 4-point line and a bunch of 2-point lines that I don't care about. So I'm going to say the address of A is 4-3 because it's on a 4-point line and a 3-point line. B is on 3 3-point lines, so its address would be 3 3 3, and so on. D is on exactly 1 4-point line. There it is. So its address is just 4. So all I'm doing is I'm recording these lines that have more than 2 points that contain the different points in my configuration. So the question is, can you make a finite set of points in the plane where each point has a unique non-empty address? And I was trying to figure out if this was a good problem. I ended up giving it to Derek, who's a terrific problem solver. And what he did was he tried some small examples, which is sort of the way you want to do most of these problems. He couldn't find one that worked. So then he tried to prove that it was impossible. Well, it turns out it is possible, but the solution is sort of big. I think this is the smallest known solution. Each address here is distinct, but you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points in order to do it. The number of submitted solutions when I put this in Math Horizons was 0. I did not get a single person saying, oh, I love that problem, here's a solution. Marketplace answer, no, it wasn't a good problem. At least it wasn't a good problem for that venue. So you live and you learn.
Okay, we're getting a question here from
So-
the sassy chat room. How about a configuration where every point has the same address?
Oh, that's a beautiful question. That is really a beautiful question. It turns out that is not possible unless the points are all on a line. I think, and I think it goes back to a problem by Paul Erdős thought was one of the most beautiful solutions that he had ever seen. He used to present this solution when he spoke. It turns out if you have a bunch of points in the plane, it's not possible for the number of 2-point lines. Liz just said 3 points on a triangle. Yeah, that'll work. Okay, so maybe with some,
this is real time. This is happening real time. We're making history here. This is big.
yeah, she's clever. You should stick around for her talk. She's speaking later.
We're none of us are going anywhere.
Yeah,
We're
where are you going to go? Right.
But I'm also sorry for pronouncing her name wrong. Please apologize.
Oh, no, that's fine. It used to be easy for her because Ed McMahon was on the Tonight Show with Johnny Carson. Jim McMahon was a quarterback for the Bears. Are there any famous McMahons now?
I mean, yeah, I can't think of any, and I don't think I've ever seen their names visually written.
So, yeah.
Okay, follow up. What if the figure is not in the plane, i.e. you get to have configurations in 3D space?
Yeah, so then you'd have to keep track, I guess. You could keep track of lines. Maybe you could even keep track of number of points on faces. In 3 dimensions, I think you will be able to create configurations. It's really a beautiful question. Both of those questions are really beautiful because what this is saying is that from a recreational problem, you can jump into a research question pretty quickly. Mm-hmm. And the research question might be stupid, and maybe it has a trivial solution, but maybe not. Maybe it's a really interesting research question. It's kind of hard to make a living doing this, but as a mathematician, but you can sometimes take these recreational problems and really have a fun time and produce some new math.
Can I ask a silly question? Gary, do you think that the complexity of that question might have intimidated people to complete it? And maybe that's why you didn't get as many responses, because one of the things that I found when I set Math Olympiad papers for the K to 9 age group is that if there is I'm just trying to think, if there's something to chew on, then they'll dig into it. But the minute it looks like it's a little bit beyond them, they actually back away completely. So do you think that maybe that might have been something that worked with that particular problem?
Maybe. I think your point is excellent. Writing a problem in a way where you try to you want it to be so inviting that people will read it and they won't quit halfway through it. So it's got to be short. And if there's a picture, that probably helps. It's possible that this was too complicated for this kind of an audience. Obviously, you don't know until you ask the question. One thing that's a little bit funny about this, there's a guy named Stan Wagon. Some of the people in the audience probably know the name. Stan has written some really interesting books, co-authored books on problems. He's got his favorite set of problems. He also sends out sort of a sporadic weekly, here's a problem of the week, or at least he used to. He saw this problem and he thought it was such a nice problem that he used it for his problem of the week. And the solution that I showed you, I think, is from one of the people who solved it, but he only got 2 or 3 solutions. He also picked up that gas tank problem. He liked that. He asked me if there was a solution that didn't use that fancy theorem of Dirichlet, and unfortunately, I don't know of one. So even though the problem itself wasn't good for Math Horizons, I think it's a nice problem. And if I had to do it over again, maybe I wouldn't have put it in there. Maybe I would have tried to do something else with it. but
I
you
mean,
live and learn.
if I can just say, I mean, I think it's a great problem, but I might not have taken it to the next step. I might have just presented, if you go back to that, the little graph that you had there, I might have presented that picture and then asked, how did I get the address of each of those points?
I see.
So what that would do is then open the discussion in terms of what are you actually doing, and get the students to understand the fundamentals of what it is. And then you start asking, what are the chances that maybe 2 of them will have the same address? What are the chances that maybe 3 of them will have? So once you start following the logic, then I think you can hit them with a bonus, the tough question, and you might get a few more who jump to the challenge.
That's if I were teaching and this was a problem I wanted to present, or if I were doing this in person and this was the only problem I was going to present, then I think that's a great idea. So anytime, and I think it's a really good point. Anytime as a teacher you can get students to take ownership of something, it's much better to have them do it than to watch me do it. I mean, watching somebody else do stuff is well, unless you're watching world-class athletes do their world-class stuff, is probably not as exciting as doing it yourself and thinking about it. And once you do it yourself, then you own it. I mean, it's in your brain, and it wouldn't be possible to do that in a journal posting a problem, but in person certainly.
Well, I
All right,
think
can I slip in a quick question, a quick comment?
Sure.
I'm Peter Mark. I'm one of the hosts later today. In fact, I'll be introducing your wife. But I happen to have with me a fun little model of a configuration where every address has 5, each point. Well, how do I want to say this?
Can everybody see Peter?
Every point has, oh, do I have to share my screen?
No, we can see you, but the view right now is the person who's talking is whose video shows up. So just so you know.
Well, here, every line meets exactly 5 others. And each point has just 2 lines attached to it that intersect it. So it's, I guess, an example of, in 3 dimensions, something where everything is the
same.
And it's known as the Schlafly double six. I came across it in a college course on non-Euclidean geometries.
Wow.
It's a kind of a cool thing. And it's a subset of the 27 lines on a cubic surface, in which every line intersects 10 others, and which is also very interesting and has a lot of very interesting symmetries to it.
So sort of the reverse problem. I'm looking for something that's basically got no symmetry, and you're talking about things that are at the opposite extreme.
Right. That's why I was the one who asked the question.
No. It's I really like symmetry too, and there must be some way of maybe taking either a platonic solid and looking at sort of a skeleton, or doing something with a Cayley graph. Those things have lots of symmetry, and getting things that have these beautiful properties where maybe the addresses are all the same, or maybe there's only 2 kinds of addresses, that kind of thing.
Right.
I think it's an interesting question. I really love finite geometry, discrete geometry stuff.
Yeah. Mm-hmm.
So now, with just we have about 8 minutes. I love all this. I don't know if you had more stuff you wanted to get through. I know people have questions. I know I have a few questions. So where are you at?
Let me get through 1 or 2 more things, and then I'll throw it open.
Sounds great.
Okay.
But I think I feel like you're really, it's so funny. Obviously, you're working through problems, but you're already kind of living proofing exactly what an interesting problem is, right? Like everyone's arguing, and that's probably a good sign. You want people to argue, I feel like. Get heated.
Oh, yeah. If you can get people back and forth. One of my favorite stories was one time I was arguing with a problem with my wife, and I said, "This is true." And she said, "I don't believe you." And I said, 2 weeks ago, I thought it was false, but you were the one who convinced me it was true. So you get this sort of taking different sides and convincing people of one thing or the opposite. And that's what makes math fun, when it's a human activity, when you're talking to people. It's also fun to work by yourself. I really like having students work in groups, but as a student, I hated working in groups. I like working collaboratively now. It took me a while to grow into that. I don't care about this problem right now. I love this problem, but the idea here is that in the journal, I don't feel comfortable publishing something that's sort of a well-known problem. On the other hand, I don't want to deprive people of seeing these beautiful old problems. So I had this carousel, which goes around on a playground. So an oldie but goodie. So the idea is at the beginning of the column, we would put in a question that had a fairly short solution that we thought had a nice aha in it. And then you'd put the solution at the end of the same column. So I wasn't asking readers to submit solutions, it's just something to look at. Here's a quick warning. A lot of you have seen this problem before. This is a very easy number game. If I start with an even number, so somebody hands you a positive integer. If it's even, you divide by 2, and if it's odd, you replace it by 3 times the number plus 1, and then you repeat. Notice after you do that, the number will be even, so then you'll divide by 2, and you keep going. For example, if you start with 20 to 10 to 5, now 5 is odd, so I have to do 3 times 5 plus 1, which gets me to 16. And then 16 is a power of 2, and that's sort of a happy place to sort of go down because I keep dividing by 2, so I end up at 1. And when I get to 1, I stop. If I start with 27, this is what happens. 27, 82, 41, 124, 700 is in there, 1,400, 3,000, 9,000. Somehow, this thing is blown up, but it eventually gets down to 1. It took, by the way, 111 steps to get to 1. So the question is, does this always reach 1 for any input number that you start with? You call it the 3x plus 1 problem. And the answer is that no one knows. One of the things that, when I was reading about this problem, I think the problem goes back to the 1950s. There was a rumor that it was problems that Russian mathematicians invented and popularized in the United States. And during the Cold War, people said this was the Russians' way of stopping all mathematical research in the United States because all the mathematicians were obsessed with this problem. And, 70 years later, it's still open. No one knows. There's a lot of stuff that's been published on it, but nobody has an answer in terms of whether this always works. A lot of numerical evidence, but you can't check all in one by one on a computer. So that's just sort of a cautionary tale. The last thing I want to talk about, and this will be quick, is the November 2015 issue of The Playground. This is a wrap up. I'm going to zoom in on what's in the bottom right here. That's there. So that was problem 322. So that was a problem. And then these were the solutions that came in. So when they came in, I would write up and I would say, here's the people we received solutions from. One of the people was Christopher Havens. And his stuff came in an envelope and it was stamped. Everything else came to me electronically. So I was thinking, wow, this is kind of an interesting guy. So I started sort of corresponding with Christopher. By the way, I only found out about 2 weeks ago that Christopher prefers Christopher and not Chris. And he talked about Pi Day at the beginning of today. In 2017, the prison sponsored Pi Day. The Prison Math Project sponsored Pi Day. I went, and so did 2 Italian mathematicians who've collaborated with Christopher on a research project. One of the events of the day was a pi memorization contest, and one of the prisoners got over 450 digits of pi memorized. In Math Horizons in 2018, I wrote up sort of what happened that day and a little bit about his story with Lucella and Umberto, the 2 Italian mathematicians who were also a married couple who worked with Christopher. And from that, here's a last problem. I'm not going to talk too much about the problem. This one, though, I do want to mention is a joint problem with an undergrad at Lafayette who was taking an abstract algebra course from me, and halfway through the course accused me of saying, "Your problems are boring." So I said, okay, I'll give you a better problem. And that problem turned into this circular dial problem. Started out as a group theory problem, but then we stripped the algebra away. The idea is you're pointing at, you have some dial and you click these things around and it starts at 1 and then it clicks to 2, then it clicks to 4, then you skip 3 and you click to 7, then you click to 11, then 5 more. 1, 2, 3, 4, 5 gets me to 4, and then 6, which gets me to 10, and so on. it turns out this thing cycles back to 1 before I hit all of the numbers doing this, each time adding 1 to how far I'm going to turn this thing. And the question is, what numbers are go through? If I have 12 numbers on the dial, it's going to cycle back, and I'm not going to hit everything. So if I have fewer numbers on the dial, if I have 1 number on the dial, it works. If I have 2 numbers on the dial, it works. If I have 3 numbers on the dial, it would go 1 and then 2. And then if I skip 2, I would jump over 3 and go back to 1. So 3 is bad. 4 is good. If you do some experimenting, those are the good numbers. And let's get back to where I was. So that's the solution. But the thing I wanted to mention about this problem is this problem appears not only in Math Horizons, but it appears at the end of an article in Popular Mechanics that came out 3 weeks ago about Christopher's journey. And this, I think his story is so inspiring. It's inspiring to me. It's inspiring to other mathematicians. I hope it's inspiring to people who are not mathematicians but are interested. There's been a fair amount of play for Christopher in the press lately, in pop culture. The last thing I would give you in terms of parting advice, just for problem solving in general, is if you're looking at a problem, if you get an idea and you think the idea is good, but even if it doesn't work for the problem that you're working on, save the idea somewhere. It might work on another problem. The other thing I would say is, if you're given a problem and you're stuck, one thing mathematicians love to do is they change the problem. Oh, I've got a solution, but it doesn't work for this, so I'll change the problem. You can't do that on a test, by the way. And then finally, just a wish for a happy Pi Day for everybody, and thanking everybody for being here.
Thank you so much. That was so fun. You know what? As someone who has a love-hate relationship with word problems, aka me, this was really, really nice to hear. I think it's so funny because I deal with teenagers. That's what I do. I work with teenagers, most of whom hate math. And word problems always come up as the thing that they're struggling with, that they hate. And the reason really is because we only want one solution from them. We're demanding one solution. And if they're on the wrong path, they get like slapped on the wrist. But the way you're presenting it is you're so excited about the solution you personally haven't thought of, right? Like you want them to say something you haven't thought of.
Oh, absolutely.
And I wonder, I mean, I don't want to cut too much into Timothy's time. I know he's ready to go and up next, but I wonder if quickly you could, for anyone watching who might be a younger level teacher, how can they bring that approach into a lower level math class, not at the university level, where emphasis is still so, placed on getting the right response, but how can they bring this joy and wonder of just experimenting and being curious?
That's a great question, and it's really hard. It's something that teachers talk about all the time. One technique I really like is you start class with a problem that is maybe a little bit challenging for the students. Maybe there's some stuff in there they understand. Maybe there's some stuff they can do. And then over the course of the class, you give them time to work. Then you bring them back, and then you try to pick out the ideas that they have, and then you put them together, and then you give them, you push them back into their little groups, or maybe new groups. I like separating people into groups by, it is sort of a high school thing where I'll say, I want you to get up, and I'll assign them a group. And maybe there's 2 or 3 people in their group, and I want them to get up and walk across the classroom. The reason for that is that the act of standing up and walking around really stimulates the brain. It also wakes them up a little bit.
And makes them feel like they're going on a mission. Like, do you know what I mean? They've got something exciting to do, an adventure.
When you get a solution that's a new solution that's better than what you were thinking of, if you can praise the student, boy, does the student feel good.
Yeah.
Yeah. It shows the other students. Yeah.
No, go ahead.
Also shows the other students that I'm sort of not wedded to the only way to think about the problem is the way I'm thinking about it.
Yeah. Well, thank you so much. I would love to say so much more, but I'll find you. That sounded like a threat, but I just meant I'll email you. I really, all of you have so much joy in what you're teaching. And I think it's so funny, me looking at it from the perspective of, high school and younger education, that it takes up until, people reach university to get that joy of mathematics. And that's a real issue, because it turns so many people off. It should almost be, well, it shouldn't be the other way around. It should always be joyful, but anyways, thank you so much. Thank you. That was amazing.